Thank you. Good afternoon, and welcome to Just-in-Time Analytics and the Need for Autonomous Database Administration. My name's Wes Haller. I'm the Chief Architect at Algebra Data. What we do there is we make technology for autonomous database administration, which is what this talk is going to be about today. So, Algebra Data, real quick, we are the data algebra company. What data algebra is, in a nutshell, is a novel application of set theory to data management. It's a stack of algebras that allow us to formally, granularly, unambiguously represent all kinds of data, relational, hierarchical, graph, as well as the queries and transformations that apply to it. And if you want to know more about the data algebra part, I would implore you, go to the website, download an electronic copy of that blue book right there. So, today's talk, two things. One, just-in-time analytics and why it needs the second thing, autonomous database administration. When I say just-in-time analytics, what I'm talking about is really two things. One is accessing data in its native format, where it lives, when you need it. And the second is using a general purpose compute framework like Spark to access and transform that data as opposed to a pre-established purpose-built system like the traditional data warehouse. By autonomous data management, what I mean is taking the manual, traditionally human-driven aspects of data management and instead using intelligent agents in combination with automation techniques to do that automatically instead. And while I usually love to save the punchline for the end of a presentation, I'm going to spoil it and get to the point early, which is simply this. Autonomous data management is a key ingredient in making Spark great for SQL analytics and taking that last holdout, which is the data warehouse, and bringing it into Spark along with all of its friends. So if you're a data scientist or an analyst, you already know that you have a lot of responsibilities. You have to take business problems, turn them into predictive models. To do that, you have to have a deep understanding of statistics and machine learning. And then to make concrete implementations of that, you have to know about big data systems and as well as traditional database management systems. And on top of all of that, there's an expectation that you're able to turn that around in a reasonable amount of time, right? Your round trip time has to be short. You have to take a problem from inception, where you have the business question, to an answer in a short enough period of time that the business can take action on it, right? So to do that, it's not easy making models. It takes a lot of iteration, a lot of trial and error, and there's a dependency on a low latency, efficient system to be able to get that round trip time down enough to do this. So what's unfortunate is, with all that on your plate, you shouldn't have to also require intimate knowledge of how the nuts and bolts of the compute layer underneath work so that you can get that low latency and that efficiency to get through the iterations quickly enough to get your job done. So Spark, fortunately, gets us a lot of the way there. It has several things that make just-in-time analytics a much closer possibility than they were before. First is it has a unified set of APIs, right? So there's the data frame, data set, and SQL APIs for declarative querying and transformations. There's the RDD API for traditional batch. There's ML, streaming, and graph. And those declarative languages, the data frames, the data sets, and the SQL layers are declarative, and what that enables is that comes with Catalyst. And now Catalyst can work on the optimization component. It can push filters down, push projections down. It can now, with the CBO stuff, the cost-based optimization that's coming in 2.2, it's going to be able to do a better job reordering joins, taking a lot more of the responsibility of writing how you want the processing to be done instead of just writing what you want to be done, taking that responsibility away from the analyst and doing it automatically. Combine this with schema on read, which is applying structure to the data when you start using it, when you need it, as opposed to having a pre-established structure, right, in a traditional database management system. And being able to do that with a wide variety of heterogeneous data sources, anything that has a data set reader and writer capability for it. And this gets us much closer to the JIT analytics use case. Also is elastic compute. And what really enables this, the ability to be able to shrink and grow your computation independently of where the data lives, where the storage is, that is what gets us the ability to be able to shrink and grow the computation, right? So data storage is over here in an object store or a database management system, wherever it is, and we can spin up multiple clusters, bigger, smaller, different node sizes, independently of where that is. Also today, right, there were announcements about serverless and also the cost-based optimization stuff that's coming in 2.2 that all go a long way towards making the just-in-time analytics look a lot more attainable using Spark. So while the compute part is starting to look sexier and sexier, unfortunately there's still challenges that remain on the data management aspect side of it. Where the data is, getting it to where it needs to be, when you need it, in the right format to be able to process it efficiently. So what ends up happening still a lot of the time is while your ETL, your feature discovery, your ML, all this stuff's happening in Spark, to do things like interactive ad hoc querying or exploratory type work, you end up exporting the data into a traditional data warehousing type solution like Redshift or something like that, and you have this cost of the glue code and maintaining it that you've inherited as a burden, right? So the bottom line is you end up having to worry about putting the data in purpose-built systems when you need to access it that way, but then bring it back to general compute systems like Spark when you need to access it that way. And data scientists end up doing data maintenance work, database administration type work, which is no bueno. So database administration in total, that's a lot of different things, right? That's capacity planning, it's configuration management, it's a billion other things, and just a shout out to DBAs, I know how much your job encompasses. I'm really just gonna pick on one part of that today, and that's the performance tuning aspect of it. So we'll focus on the performance aspect, keeping the systems that we're working with healthy and making them perform well so that we can get that iteration time down. What it means to do the manual work to keep these systems happy and healthy and reduce latency is things like maintaining indexes, right? Building the right indexes in the first place, dropping indexes after they become irrelevant. And the analog to that in Sparkland would be having data partitioned correctly so that filters can be pushed into it by Catalyst and so that you can avoid unnecessary shuffles or very high network congestion during shuffles, right? It's also things like materializing views, pre-aggregating data, moving data sources from hot to warm to cold storage, and then a lot of configuration management in between. A couple Spark-specific aspects of tuning that you do manually today would be the key with Spark is keep workloads in memory, right? If you don't keep workloads in memory, bad things that rhyme with OOM can happen. So what we do is we end up segmenting data frames, we segment queries, we'll cache, and we'll checkpoint, we'll use persistence as a way of helping create DAGs that have reasonable places of rest and that put some boundaries around where the operations can be reordered to keep the workloads in memory. It also, of course, means configuring cluster parameters, but you've heard a lot about that today already, okay? And then my favorite, which is the Spark SQL shuffle partition setting. So with the RDD batch API, every shuffle type operation, you get a chance to describe how many partitions the output should be in when it's done, right? What it's really about is how big should each piece of that be so that when those are the inputs to the next stage, again, you can keep the workload in memory, right? But with the Spark SQL and dataset APIs, so the declarative ones, you really don't get to do that for every shuffle operation. Your most granular level of specification for this is going to be on a per action basis. And that's because Catalyst has to have enough room to be able to reorder instructions to do what it does, which is try to throw data away early as possible, right? But even when you can set this thing, and the default of 200 is never what you need, it turns out to be difficult to compute. It's dependent on data size. It can be affected by things like data skew. It's dependent on what you're doing in the queries, and it's also dependent on hardware, right? The number of executors, number of CPUs per executor, the amount of memory per executor. And so even if you figured it out through trial and error in a long process for whatever your staging environment was, when you move to new hardware or the data size changes because you're using the real data now, you have to start over again. So the problem with manual tuning, in a nutshell, is it's a lot of painstaking, difficult, long trial and error, and things like the data changing, the queries changing, the hardware changing, things that are by nature really dynamic in this just-in-time analytics environment. Those things really exacerbate these problems, right? In a nutshell, manual tuning just stinks. It's not fun, and it ends up eating a lot of our time when we really want to be focusing on getting our jobs done, building those models, getting answers. So let's get to the fun part, which is a motivating example for autonomous data management. How would we do this? As a specific example, we're going to look at speeding up queries by detecting patterns among them where we're going to find an invariant in a stream of queries that perhaps we're doing some interactive work, right? And there's some kernel of a query that we've made, and we're going to refine it over time. We're going to ask variations of that same question. By the end of the morning, we're going to have gone through 300 iterations of submitting this to Spark, and there's going to be like 50 CTEs on top of that initial kernel. And so we want to factor out this invariant and materialize a view to avoid redundant computation and get our latencies down so we can get through iterating on this in a much shorter period of time. If we look at these obviously super duper complicated SQL queries up here, at first glance they may not seem to have a lot in common, but there are a few similarities. They share a predicate term that happens to be a conjunctive term that means we can factor it out into its own filter. And they also share a join expression. It's a little less obvious in the third query because the lexical ordering of the join puts A and D joined together first. But you can see because join is pseudo-associative and pseudo-commutative, we can reorder that join expression and see that there is still a join between A and B on the same constraint as before. And what we could do, and would do manually, is factor out this invariant portion of the query and rewrite each of those three in terms of that invariant, right? Best is we would materialize that inner part, so we would persist that data frame and rewrite our queries in terms of that persisted piece, right? But since this is about autonomous data management, what we really want to do is have the system do this part for us. So there's a couple components that I have to introduce to talk about how we ended up doing it at Algebra Data. I already mentioned data algebra. And I said that on top, with data algebra, we could represent relational data systems, right? In fact, we do. We built a model for SQL that faithfully represents SQL. We uninspiringly called it SQL data algebra, or SQLDA. And SQL can be translated to SQLDA, and SQLDA back to SQL. Once we have that, we like to represent this as a graph data structure. And if we put this all into a composite graph data structure, which we'll call the entity store, we begin to build up a model of how all the expressions that we encounter are related to each other. We can put metadata on top of that in terms of timing and user. We can put a scoring model on top of this and talk about usage. And we begin to have the nuts and bolts to build a predictive model around answering the question, based on what we've seen so far in terms of queries and data frames, what are we going to see in the future? And with that, we can build an optimizer on top, where that optimizer is going to employ different strategies to try and match these techniques for doing data management and reducing the amount of resources needed, reducing the amount of time required to compute these queries with this predictive capability, looking for patterns in query streams. So, review this part real quick here. We have SQL, we turn it into some math, and we use a graph to represent that, right? And that's like the next 5 slides are SQL, math, graph. So we start with an empty entity store, right? And we have a SQL query. There's some foos, some bars, some bases in there. We're going to take it, translate it into a SQLDA expression graph, and we're going to analyze how that graph relates to the entity store. There's nothing in the entity store right now, so we're going to put all the novel sub-expressions in that query expression graph, which is all of it, into the entity store. We then run the optimizer, which is an evolutionary algorithm style thing that tries different ways of finding routes to optimization possibilities. And it's not going to find anything to do here. So as you would expect, when there's nothing to be done because there's no pattern that's discovered, it's pretty neutral. It tosses this back over to Catalyst and Spark, and it computes, and it's done. Over time, though, because we're in this interactive scenario, right, where we're kind of riffing on the central theme, we're going to submit more queries that resemble that last query, even if not in an obvious way, right? Translate them to a data algebra graph, analyze them. Again, the novel pieces of the expression end up being added to the entity store. And you can see it's turning into an honest-to-God graph now. It's got multiple roots, there's reconvergence and fun stuff like that. And new queries come in, and the graph is becoming more and more rich, and we're collecting that metadata on it. And eventually we start to have some evidence that bar and baz are kind of special, right? So this is kind of like a heat mappy sort of visualization of what you'd imagine that metadata is going to look like. And at this point, we collect enough evidence that this, in combination with the optimization mechanism, gives us the courage to go deploy an optimization. We're going to go materialize that view by factoring out those invariant pieces of the query. All right, so we materialize the view. We now have that equivalent representation of what was a SQL query or a data frame program. Now it's an actual data frame that connects to a materialized view piece of data that might be just in memory in the cluster. It might be off in durable storage in an object store like S3. And we rewrite automatically queries that continue to match this pattern in terms of that materialized view. So where this gets interesting is those were obviously not very complicated queries, and it was sort of obvious how to do this. But the more complicated the queries, the more that's going on, the more queries you're generating, the more analysts are concurrently using the system, the more difficult this gets, and there's a reason that this is hard work for a human being. But what we've done is we've gotten to a point where when we start to address some of the problems in here, reordering the expressions to be able to exploit this sort of data algebra graph view of the system to find where equivalence exists, we can turn SQL queries or data frames into lookups into a cache system, right? So this is good because it makes things go faster. When we are able to substitute a materialized view, instead of recomputing the result over and over again, the latency goes down, and the number of resources, so the number of executors that you would need, right, the size of those executors also goes down, which saves money and time. But probably more important than anything is this is not just happening and speeding things up, it's happening without the analyst doing anything. So the analyst gets to focus not on performance tuning, but in fact on doing their day job, which is answering business questions by making models. This, as I mentioned, is actually a thing that we're working on at Algebraics Data. In fact, there is an implementation of this style of autonomous data management. The way we chose to do it is actually to shim the PySpark API. So instead of importing from PySpark, you import from AquaSpark. You would write a data frame or SQL-based application the same way that you would before, except the difference is when an action is encountered, we intercept the analyzed logical plan from Catalyst, translate it into a data algebra representation, compare it against the entity store, run the optimization strategies against it, spit out a new set of SQL queries, and interestingly, we hand those over to Catalyst. So we still rely on Catalyst to do the single query optimization part of this, right? Predicate and filter pushing, join reordering, and that kind of stuff. Where Catalyst is concerned with single query optimization, sort of a traditional way, the autonomous data management aspect is looking for patterns and streams of queries and instead rewriting them to benefit a family of queries, right? So this is just a narrow slice into this, and there's a whole lot more about, how do you actually tell when two expressions are equivalent, right? What other tricks are there besides just caching a materialized view? There's a lot to talk about. This is what I've been working on for the last several years, and super happy to talk about it in questions here, or you can contact me afterwards. But the wrap on this presentation is simply this, right? If we take a mindset that where we should be pushing this set of tools, right, is towards autonomy, where the system's doing more and more, and that could be the serverless compute stuff, right, with Databricks. It's building better optimization for single query optimization, and it's also taking the data management aspects of this away from the responsibilities of the people who are trying to make models answer questions. Then we can make Spark sort of the one-stop shop for everything analytics, right? In a nutshell, autonomous data management makes Spark great for SQL analytics. It moves that last holdout, the data warehouse, into that realm. So again, super excited to talk about this stuff ad infinitum, in fact. Please ask questions, and shameless plug, if you're interested in trying it out, contact the fellow on the right-hand side of the screen there, or go to our website. And thank you very much.
So we have a microphone set up there, or I can run over to you if you'd like to ask a question. I can start us. I had a quick question. So I'm curious, with the cost-based optimizer appearing in Spark 2.2, like will your your data algebra system does it currently take any data sizes or statistics into account? And would you, if it doesn't, have you? I don't know too much about the cost-based optimization, but I'm wondering what the integration points might be.
Right, that's a great question. So, in complete honesty, the way that the system is architected is somewhat agnostic of what the compute system underneath it is, right? So it's not Spark specific after we've translated the queries and the data into a data algebra representation, right? But when we do the cost-based decision making, which that's what this is about. It's sort of like, when you're going to go materialize a view, you really want to know, is it going to be worth it to bite off the initial cost of materializing that view so that over time, the next n number of queries that are run that match that same pattern is there going to be a net gain, right? That's a cost-driven decision-making process. So our costing system does have to faithfully model what Spark does. Definitely an integration point I think exists is the statistics gathering part of it, which the guys who worked on the CBO stuff spent a lot of time on, and that would be easily something that we would slurp in as an integration piece there, is reusing the statistics gathering part of the CBO stuff in Spark.
Cool.
So as you're accumulating these graphs and the associated views, is there also some rate at which you drop them or forget them?
That's a great question. Yeah. So if you were paying attention, and it sounds like you were, yeah, the stuff's somewhere, right? It's in storage somewhere, and so over time, it makes sense that you wouldn't want to just keep filling up S3 with a bunch of materialized views that are no longer valid, right? So similar to the algorithms that we use to find the evidence and reach a confidence level where we want to create these things in the first place. It's actually really similar to the algorithms that we would use to also sort of notice there's a hit ratio here, right? Like there's time information that's metadata on top of the expression store. And so there will be things that will not have been accessed in a long time and were not very useful and maybe could be computed again without the whole world catching on fire. And those would be like the highest candidate things to delete, right? And then it kind of goes down from there in terms of a ranking.
Sorry, just one more question.
Absolutely.
Do you have anything on your roadmap for providing like a similar Scala/Java shim?
That is on the roadmap, yes. So right now, the specific incarnation of this is Python specific, and it's for data frames and SQL, but Scala and Java are on the roadmap as well.
So we often move data out of like an S3 or HDFS into, say, Redshift for this purpose. Like we want faster access to this data and we know it. So we're sort of like manually, right, optimizing by materializing view in another store. Is that something the system could be aware of, that, hey, there's not only materialized view, but it's in a store which is maybe going to be faster than going directly at S3 and taking advantage of that kind of optimization?
Yeah, it's definitely something I think about a lot. So it's not what it does right now, but it's generalizing how heterogeneous storage works across the board in terms of how immediately accessible something is, right? I mean, it's the same way that we program HPC stuff when we're looking at, cache, memory, and permanent storage, right? And because MPP systems like Spark are making it so easy to integrate these things from a can I get to it perspective, I 100% agree that where this needs to go is modeling that as part of the equation for where should data go, right? Just because it exists in a certain area doesn't mean that's the best fit for it, doesn't mean it's the best format for it, and it easily falls into that camp of why do you as the guy writing queries care, All you want is for it to come to you when you need it in a quick manner, right?
Yeah. So like a follow-on is maybe more tangible, which would be if there is even, say, a materialized view that somebody's built by hand, the system isn't aware of it. Is there a way to make the system aware to say, hey, you know what, we have a table that's very similar to the one this query is asking for, this partition in a better way, right? I mean, I don't know how many queries I look at and I just manually walk over to somebody and say, hey, change that table out for that table because then it's partitioned correctly and it's going to go a lot faster. But
yeah,
it's just
okay.
like tribal knowledge, right?
Yeah. So, I mean, what you're noticing there is that's kind of how it works right now, actually, doing something like repartitioning. The catch is it depends on how much you want to give up in terms of the freedom of your data, right? If you really want it to be like your object store is like a file system and you can just delete data, or you want to be able to access it at that location whenever you need it, then there's certain things that can't necessarily change, right? But the more control you cede over how you can access the data, that doesn't mean you can't have lots of flexibility still, but if the system's at liberty to make a copy or change how it's represented, perhaps in an equivalent way, but just partitioned differently, there's a parquet with the same name, with the same key position in S3 or something like that, you can get a lot of mileage out of that.
Thank you.
Actually, I had another question. I'm curious what other systems you've applied this to outside of Spark.
Okay. In the past, actually, at Algebra, we've applied the technology, like the algorithms and techniques, to a couple databases that were created in-house. And one of them was a relational SQL system that was a single node type system. The other was actually a Sparkle RDF system, right? And generally, that sort of workflow, that pipeline of building up that graph of how expressions relate to each other, looking for patterns, that stuff is pretty independent of whether it were relational or something else.
So once you get it into like a data algebra model, it's all the optimizations sort of hold over whatever system. So you have some input and then some way of emitting. I guess I had a follow-on question of, are you emitting SQL or actual like logical plans?
Yeah,
I guess they're close.
The way we implement it is actually literally to take the analyzed logical plan out. That's sort of the it's the junction point where both the SQL path and the data frame path come together. It's also where Spark did some of the hard work of ferreting out aliases and stuff like that. So we take the analyzed logical plan, normalize it a little bit, and that's directly what we translate from into the data algebra representation.
And then what are you emitting back to Spark?
SQL.
SQL, okay.
Yeah, so a curious sort of side effect of that is you could have actually written a data frame, Python-based program, and what ends up being put passed to Spark is actually an equivalent SQL representation.
I see. How do you, in that case, how do you handle things like UDFs?
What's that?
Is there any special handling for something like a UDF?
Okay, yeah, very good question. The main constraint is this. to do caching, we have to be able to comprehend that a UDF or any operation is pure, right? It can't have side effects, and it has to exhibit referential transparency. It has to give the same answer every time you call it. Outside of those two things, the UDF would just work, right? So as long as when you register the UDF, we know those two things about it, and it's specified in the same level of detail as a normal operation in the system, then we can still reason about it from a caching perspective.
Well, I think we're right at the end of our session, so I'm sure you'd be happy to take more questions offline. But other than that, I think that's the end of this track for the moment. I think it resumes again at 4:20.